Hi there, welcome to today's video. I am excited for today's video because we are going to learn how to train a logistic regression model from scratch. When I say from scratch, what I mean is we are not going to use any libraries such as sklearn. We are actually going to build the model from ground up and understand what is inside the model. So let's get started. Logistic regression is a machine learning model that is used to solve classification problems in the context of supervised machine learning. Some of the things that we need to know is what is a sigmoid function and what is the cost function used for training the logistic regression, and how do we use gradient descent to train the logistic regression model. And we will learn some of this in this video. As a first thing, let's preview what is a logistic regression model. So let's say we have a data set that contains 4 samples, and each sample is represented by 2 features, x1 and x2, and it has a label. So in this case, the 3 of our samples belong to one class and one sample belongs to another class. So we have 2 classes, the binary classification problem that we're trying to solve. So let's try to fit this into our logistic regression model. We will just take one sample and try to fit that. So logistic regression is derived from linear regression. So we'll start with the linear regression equation, which is this. So in this case, W0, W1, and W2 are model parameters, and we do not know what these are. But we do know what is Y, we know what is X1 and X2. So then, to derive the logistic regression from linear regression, what we do is we take this Y and we pass it through a sigmoid function, which is 1 over 1 plus e to the power negative 5. When we pass it through a sigmoid function, what we get is y bar, which is a number between 0 and 1. It is essentially the probability of model's prediction. Then when we get this y bar, which is a number between 0 and 1, we put a decision boundary. We say if this number is less than some threshold, such as 0.5, then the outcome belongs to one class. If the number is greater than or equal to 0.5, then it belongs to another class. So this is logistic regression. Now, I want to go back and go over these 2 equations since I have them here. So these 2 equations are nothing but just matrix representation of our first equation. So let's look at them closely. So here I can rewrite this W1 x1 plus W2 x2 as a multiplication between 2 matrices. The first matrix is matrix of model parameters W1, W2, and second matrix is the matrix that contains the inputs, in this case input features x1, x2. So when I multiply these 2 matrices, I get W1 x1 plus W2 x2. So that's really what this is. And this is the same thing, except that I compressed this matrix W1, W2 into a variable W, and I compressed x1, x2 into variable x. So this is logistic regression in the context of one sample. Now, usually, when we try to do a prediction, we want to process all of this data at once. We want to take all of these samples and we want to make a prediction, which in this case is y bar and eventually y predicted at once. And the way we do that is using matrices. So we take this X, which is all of this data set. Our data set contains 4 rows and 2 columns. because we have 4 samples and each sample has 2 features. So this is our data set. So we take X, which is 2 by 4, then W will still be 2 parameters because we have 2 features. So the model parameters are going to be the same as number of features, which is 1 by 2 in this case. Then W0, which is a bias, will be 1 by 4. So let's say you are choosing bias as 1. This will be just be a matrix, but it will be just 1, 1, 1, 1. And if we solve this equation, we get this Y, which is a matrix, and it will be of the dimension 1 by 4. And the things that are in this matrix are the Y value for each of these inputs. And then we take this Y and we pass it through the through the sigmoid function, and we get the answer. So this is how we process all of the data at once, and this is what we'll be using when we go to code this. Okay, so far we understand what is our logistic regression model and what we are trying to learn. So now next step is, how do we learn? So for that, we train a machine learning model, and the framework for training a machine learning model looks like this. Since we do not know what are the model parameters, we start with a random set of parameters. Then we repeat this step 2 for n number of times, and we call each iteration as an epoch. That's one way. Second way is we repeat this step until some criteria is met, which we will discuss in detail later. But for now, let's keep things simple, and let's say we repeat this for n number of iterations. The question is, what do we do inside each iteration? So inside each iteration, we take this model, which currently is built using random set of parameters, and we try to predict the output for all of the samples in the training set. Then we make that prediction, and we want to know how close or far that prediction is from the true label. So for that, we find an error, and it's also called the cost function. And our goal is to minimize that cost function, right? Because we want our predictions to be as close as possible to the actual label. So for all the samples, we predict the value and we find the error. Then we take the average error for all of the samples. Then our goal is to minimize that cost function. And the way we minimize this cost function is using gradient descent. And we will study in the next slide how we use gradient descent to minimize the cost function. And once we do that, then we update the model parameters and we repeat this step for n number of times. And eventually, what we get is we get the model parameters that satisfy our problem, and we have our trained model. Now, the question is, what is this cost function? Now, if you remember, or if you have done problems with the linear regression, you probably know that for linear regression, we use mean squared error as a cost function. In this case, however, we define a cost function that looks like this. Don't get scared, because we will break this down into parts and understand why this cost function makes sense for logistic regression. Now, this is a graph of negative log. As we can see, if the value is, let's say we are finding a log of a small number, the result will be very big number, right? So that's the fundamental thing that we need to know why we use this cost function. So let's look at it. So let's say your true label for a sample is 1, but the model predicts a value close to 0, which means the prediction is far from the true label, then in that case, negative log of y will be a very high number, which means we are penalizing the model because the prediction was very wrong. Now, on the other hand, let's say the true label is 0 and the model predicts a number that is closer to 1, then this 1 minus y bar will be a very small number, and again, negative log will be very big, so we are penalizing the model. So this is how, that's why this cost function makes sense for logistic regression. Now, in the previous slide, we said we want to do this for all of the training samples, and then we want to take the average. So this equation here is just that. So we take the average because we have m number of samples, so we divide by m, and then we are in this equation here. This equation here is exactly the same as equation here, except that we have compressed it by putting a plus sign. And then we do this for m number of samples. So these two equations are exactly the same, except that this is just for one sample and this is for m samples. Now, how do we minimize a function? From calculus, we know that we can minimize, we can find a minimum of a function by taking its gradient and setting it equal to 0. Same thing here. The way we minimize, in order to minimize a function, first thing is we want to find the derivative of a function. In this case, the derivative of the cost function that we have defined here is given by this equation. If you are interested in deriving this derivative of a cost function, I will post a link below to the derivation, but for now, let's just say we know that the derivative of cost function that we are using for logistic regression is given by this equation. And this equation is simple. So all we are doing here is we are taking the difference between the predicted and the actual. We are multiplying with the input, and we do this for all of the samples, and then we take the mean. So that is the derivative of the cost function. Okay, so now we know we have the derivative of the cost function. And question is, how do we minimize this cost function? So the minimizing is done using gradient descent. Gradient descent allows us to minimize this cost function in a number of steps. And at every step, we take a step which is defined by this variable called alpha, which is a learning rate. It tells us how big of a step we should take. And then at every step, we find the gradient. And then we use that gradient to update the model parameters. And the way we update the model parameters is using this equation. So this is our current set of weights. So to begin with, we have randomly initialized the weights. So this will just be the random initialized weights. And then we take the learning rate and multiply that with the gradient for that particular step. So this is how we update the model parameters. And then once we have updated the model parameters, we repeat this. We repeat all of the steps for n number of iterations. And that's really how we train the logistic regression model. So now let's code. So the problem that we want to solve here is I have a data set that contains a bunch of emails, and the task is to identify which emails are spams and which are not spams. So it's a binary classification problems with two classes, spam and no spam. I have already done the data pre-processing and feature extraction, test train split. So I will not go into those details for the sake of time. So what we have here is we have a training set and test set along with their labels. And for training set, I have 3,621 samples, and each sample is represented by 2 features. So if we go back to our slides, so here the X, which was the input data set, had the shape 4 by 2. So we have 4 samples by 2 features. So in our case now, we have 3,621 by 2. So that is the shape of our training set. Now let's build the logistic regression model. The first thing is we need to define some parameters. In this case, we define the maximum number of iterations and the learning rate. So if we go back to our slides again, if you look at the training framework, we said that we want to repeat this step 2 for n number of iterations. And that is what I call max iteration in the code. And then learning rate is what we use to update the parameters using the gradient descent. So that's what I define as alpha. Okay, then there are 2 main functions we need to define for logistic regression model. The first function is called fit. Usually we call it a fit function, which is used for training the model. And then we have another function called evaluate, which we use for evaluating the model. So I call it as fit logistic regression and evaluate logistic regression. So let's focus on fit function. So this fit function is going to take the training set and the corresponding labels, and it is going to implement this training framework. So as we can see, we start with a random set of parameters, and then we define a loop, and we each iteration of that loop is called one epoch, and we run it for n number of iterations, and in each iteration we predict the output using a logistic regression model that is initially based on the random set of parameters. Then we compare the prediction to the true labels, and then we find the average cost, meaning average error for predictions for all of the samples, and then we want to minimize the cost function, and the way we do that is using gradient descent, and then we update the model parameters, and we repeat this until we are satisfied with the model parameters that we get. So what we're going to code in the fit function is really just this step 2. So let's go back to the code. So I define the set of parameters, which initially is just initialized randomly. And then my bias, I initialized it to 0. It can be initialized to 1 or even random number as well. So by the way, if we go back to our slides, I know I'm being repetitive, but that is on purpose so that we learn. So bias is this W0, and the rest of the weights are in this W. So that's what these 2 are. Okay, now let's go through the for loop. So this for loop runs for maximum number of iterations. And in each iteration, the first thing that we do is we use this set of weights that we have to do the prediction. So the way we do the prediction is we want to first define this y, which is simply the initial set of parameters. And we take this parameter and multiply that with the X transpose and add the bias, and we get the Y. So that is first step. But then we are not done yet, because for logistic regression, we want to pass this Y through the logistic function, which we have here. And then Y bar is the prediction from the logistic regression. And this is a number between 0 and 1. So it represents a probability of prediction. So if we go back here, so the first thing is we are simply defining that y. So we are taking the W and multiply that with X transpose, add the bias, and then we get this term called Y in the slides, but here we call it sig term, same thing. Then we pass it into a sigmoid function, and we get the predictions, which is the number between 0 and 1. Then we find what is the difference between Y prediction and the actual label. Actual label is 0 or 1, and this is a prediction, which is a probability. One more time. The difference is simply Y predict minus Y. So far, nothing fancy. The next thing that we need to do is we want to find the average cost, and we want to minimize that cost function. And the way we minimize the cost function is using gradient descent. So if we go back to the next slide to understand what is the cost function for logistic regression and what is the derivative of the cost function, we will understand the code better. So here, we have already gone through these. So this is the average cost function for logistic regression. And we know that in order to minimize a function, what we do is we take a derivative and set it equal to 0. So in this case, though, we want to use gradient descent. And the way gradient descent works is first thing is we need to find the derivative of a function, which is this. And then once we know the derivative of the function, then we simply use this equation to update the model parameters. So one key thing to take away from these slides is we actually don't need to define the cost function in the code, because what we really need is the derivative of the cost function. So we don't need to define this in the code. We just define this derivative of the cost function to update the model parameters. So this derivative of the cost function for logistic regression is pretty simple, because it's really, we are taking the difference between the actual and the true, the predicted and the true labels. And then we are multiplying that with the input, and then we take the average. So that's really the derivative of the cost function. And if we go back at the code, we will see exactly that. So here in these two steps, we are doing what we saw in the slide. So we are taking the difference between the two and multiplying that with the X input. And then we want to take the mean. And that's what we are doing here. So we take the multiplication and then we take the mean of the result. So once we have that, then we simply use the equation to update the model parameters. So W is the new set of parameters, and this W is the current set of parameters. So initially, right now, we are just going through the first iteration. So this is just the random set of weights, and then minus learning rate times the gradient of the cost function. And remember, we also have a bias. So we also have to update, bias is also a parameter. So we also have to update the bias in the same way as we update the other parameters. Okay, so these are, now we have updated the model parameters. So then so this statement right here is basically converting the predictions, which was in Y predict, and we said that this is going to give us a number between 0 and 1. So we want to convert that prediction to either 0 or 1. Remember, this is a classification problem. So we want to convert this number into 0 or 1, and the way we do that is by defining a decision boundary, which in this case is simply 0.5. We say we say set the class equal to 1 if probability is greater than 0.5, else set it equal to 0 for all the probabilities in Y predict. So that is simply what it does. However, going back to the update parameters. So once we have updated the model parameters, we go back and repeat for the second iteration. Now for the second iteration, we are going to use the new set of weights. So this W and this bias is the new set of weights that we updated here. And then we again do the prediction and find the gradient of the cost function. And then we updated the model parameters again. And we repeat this loop for maximum number of iterations that we define. Then eventually, what we're going to get is the final set of parameters, W and bias, that we are going to use for the final model. So that's really what we do in the logistic regression model. So once that is done, then we also need to define a function that is going to evaluate the model that we just trained. And for that, we simply define another function. And this function is going to take in the weights. It's going to take in the model, the bias. So it's going to take in these model parameters, and it's going to take in the test set. And all we are going to do here is we want to define the model using this set of weights and bias. So basically, we want to define this equation using the weights that were trained using the training set. And then we want to use this y and pass it through the sigmoid function. So that's really what we're doing here. So for the first equation here is simply defining that y. So we're multiplying the weights with the input, and then we add the bias, and then we pass it through the sigmoid function. And finally, we do the prediction, which is again converting the numbers that are between 0 to 1 to either 0 or 1, and we give out the results. Okay, so then now we have done this. So let's run this and see the results. Okay, I can get rid of that. Okay, so here first I create an instance of the class logistic regression model, and I call it model underscore LR, and I give it the two parameters, and those two parameters are 10 and 0.001. So 10 is the maximum number of iterations and 001 is the learning rate. And then I call the function fit underscore logistic regression. I give it the training set and the labels for the training set. And the output is going to be the predictions for all the samples in the training set, the learned model weights, and model bias. So if we run this, what we get is we get the learned weights are these big numbers and the bias is this. And then if we try to see the metrics, let's try to get the accuracy, precision, F1 score, recall. So let's do that. Okay, so the model is doing, on the training set at least, it's doing pretty good. So we can see the accuracy is 95%, the recall is 98%, 95%. So it's pretty good. Now, the goal is to also have good performance on the test set. So let's do, let's call the evaluate function. And what we're going to give it is the model weights, the model bias, and the test set. And then we will also get the model metrics. So let's run this. So again, it's doing pretty good. So on the test set, also the accuracy is 96%, 98%. So it's pretty good. So that's really what is behind the logistic regression model. So now that we understand the logistic regression model, how it works, what is inside the model, here's the good news. So if you're familiar with the sklearn library, it already has the inbuilt function that implements actually it has a class that implements the logistic regression. So we don't actually need to code this logistic regression. This was what we did today was to actually learn what is inside the model. But if you understand this already, then why not just use off-the-shelf models? So let's see how we can implement using sklearn. So it's actually pretty simple. So from the sklearn, we import the logistic regression, and all we have to do is first we create an instance of the class logistic regression, call it CLF, and then we call a fit function or method from this class and give it the training set and test set. And then we use this trained model to do the prediction on the test set. So simple. So all you need to have is you need to have your training set and the test set ready to be given to this logistic regression class, and it will do the training and test and prediction for you. It's pretty simple. So that's all what we wanted to learn today. So if we go back to our slides, what we learned today was we understood what is the logistic regression model, what is the cost function, what is the derivative of the cost function for logistic regression, and how we use gradient descent to update the model parameters for logistic regression. So I hope this video was helpful. And if you like the content on this channel, please consider subscribing. I would love to have you as part of my channel. So with this, thank you so much for joining me today, and I will see you in the next video. Thank you.